This activity gives you another opportunity to work through producing the state space representation and transfer function representation for a system. So in this case, we're using that circuit example from 2 classes ago. The only change that we're making here is that we're explicitly calling this voltage here, V2, to be our output, Y. So you can kind of imagine that we're going to put an oscilloscope across that capacitor, and we're going to be plotting then the voltage of that capacitor over time. So that's kind of how you think about an output. There's going to be a sensor there that's going to be measuring that. And then the current coming out of that source, we're going to specifically call our input U, just to kind of be consistent with the way that we're calling U the input and Y the output. So go ahead and take some moments and work through these different representations, keeping in mind that the state space representation, our goal is to create a coupled set of first order differential equations, and that's what we call state space. And transfer function will be applying the Laplace transform and solving for the output in terms of the input. So press pause and give that a try. So again, we've got a lot to go over. So here are the 2 solutions that I came up with. There are multiple different representations that are possible. One thing that's certainly possible is you could have picked your set of states to be in a different order, and that would cause some of these entries to be in different positions in your matrices. So you can make sure to take that into account when you're checking. So let's go into each one individually. Let's start with state space. So our goal, remember, in state space is to produce a set of coupled first order differential equations. And so the thing that is tricky about this particular example is that we're already in essentially a version of state space, just kind of a messy version. So in this case, there are no higher order derivatives. And so we only have first order derivatives. And that means that we already have a set of coupled first order differential equations. So in this case, V1 dot is there, and here it's V2 dot, and here it's IL dot. And so we only have those 3 equations with the 3 first derivatives. And so really what we need to do is just reorganize this to put it into state space form. So if we pull the derivatives to the left-hand side and put all the other terms to the right-hand side, we can produce this, which now looks a lot more like state space notation. And if we define, and this is where you could easily define your variables in a different order than me, but if you define x as being v1, v2, and il, then notice these are all the things that we have derivatives of. Then we've also got all of the different coefficients then that appear in these matrices. So that's going to appear in the input matrix, and the rest of these are going to appear as coefficients in the state matrix. So from that, we get V1 dot, the coefficient there in front of V1 is just right here, because again, this V1 multiplies the first column, V2 multiplies the second column, and IL multiplies the third column. And here we've explicitly said that our output is going to be V2. And so that is why here, the 1, we're going to make Y, the output, equal to V2. And so now we're going to look at the transfer function approach to solving this problem. So this slide's particularly messy, but the process is just what we've talked about before, where we take these 3 differential equations and apply the Laplace transform. So the unknown u is just capital U of s, and each of these we just define, each of these different variables we define capital versions. And so the interesting parts for the Laplace transform are where these derivatives are, and so where those occur, we inject, so where V1 dot is, we're going to inject S times capital V1 minus the initial condition. And again, in this context, we're not going to take into account the initial conditions, but again, they are there if we were to use them. I, in fact, have missed out on putting down IL of 0 here and then canceling it out. So you get these three equations in the Laplace transform domain, and now our goal is to create the mapping between the input and the output. So we know what the input is. It was u. The output, we've been told, should be v2. So that means that in the course of combining these equations together, we want to get down to something where we're mapping the input to the output. And in fact, we want to get v2 equals something, that something's the transfer function multiplied by u of s. So that's why this whole thing ends up being in the denominator of the solution. So that's where we're going to. So that means that we want to get rid of IL variables and we want to get rid of V1 variables. So that's our goal. So here we could, we simply just consolidate some terms in V1 and get this expression, which has a u in it, which is good, but it also has a V1 and an IL. So in the second equation, we can combine some terms, which are the V2 terms. And so we're going to keep the V2 and we're going to get rid of IL. So we could plug that IL into another equation. And that other equation is this one, where we're going to just rearrange it to see that now we have this IL in here that we can substitute in. And so that's what this arrow is doing. This arrow is saying I'm going to take this and I'm going to substitute it in for IL. And so that's where we end up getting this particular equation, which is saying that V1 is equal to all of this. And this is all just algebra. And the beauty of dealing with the Laplace transform is now that we're doing algebra instead of differential equations. So now what we're going to do is pick this kind of already slightly nasty equation and plug it in up here for this V1. And then take this and plug this in for IL. And that is what ultimately gives us this large equation, which is now, we've now effectively gotten rid of V1 and we've effectively gotten rid of IL. And there's certainly many different ways that you could have chosen to substitute these in to get down to this same point. But in the end, when you solve for V2 in terms of u, you will have to get something that you can simplify down into this particular format. And so by, again, writing V of s, or in this case, V2 of s is equal to something times u, oops, capital U of s. This something is this 1 over this large term, and that is the transfer function that describes the system.